Welcome to another calculus video. In this one, we're going to look at section 4.5 in the book, Integration by Substitution. In the last section, we looked at just the fundamental theorem of calculus. This section will expand what we are able to integrate. So let me hop over here real quick. This is the assignment for this section. A handful of problems out of the textbook, and then the remainder of them will be on WebAssign. Now, before we get into this, let's do the reverse, or this is what we are going to reverse today. We are going to undo the chain rule. So here is f of x, and I want to derive it. So we are going to call this f prime. And remember the chain rule. We have this inner function that we will first derive around. So our exponent comes down, 4. And then we have our same quantity, x cubed plus x, but now it is to 1 power lower to the third. And now we need to satisfy the chain rule. So we are going to derive this inner function. So what is the derivative of x cubed plus x? Well, that's going to be a 3x squared plus 1. Now, I chose to use a different color of ink because when we derived this with the chain rule, this was sort of created out of thin air. You know, we see where this came from. It's our original problem. We moved around our exponents, lowered the power by 1, but this sort of magically appeared like a magician pulls a rabbit out of his hat. So it makes sense. If I was going to anti-derive this, I'm going to need to identify an inner function. I am going to need to identify that inner function's derivative. And when we reverse the process, remember when we derived, this was kind of created by the chain rule. So when we anti-derive, this is going to magically disappear. In the class, let's do this other one over here. Sine of 2x quantity cubed, or 2x cubed. So we want to derive f prime. The derivative of sine is cos, and it will be the cos of the same angle, 2x cubed. And now we're going to once again create something via the chain rule. The derivative of the inner function is 6x squared. So it makes sense when we anti-derive this, this is going to disappear. We'll anti-derive cos back to sine of the same 2x cubed. Usually, I have always thought of deriving as a downward process. Like if I have 3x to the fourth and I derive, begins with the letter D, down also begins with the letter D. The exponent comes down and we multiply 12x. The exponent goes down 1 power to the third. So at least in my own head, I've always thought of deriving as a downward process. And then naturally that's going to make anti-deriving or integrating as an upward process. You know, we're going to find our inner function here. It will be to some power. I'm just going to put a 3 up there. I will use the analogy, this is our rocket. We want to launch our rocket. When we do launch the rocket, the exponent will go up by 1. We will divide by that new exponent. And then we're also going to need the inner function's derivative. Whatever this is, the derivative must also be present. And remember, this is what's going to disappear in the whole process. When we anti-derive, this inner function's derivative will disappear. I call that the rocket fuel. We cannot launch and send our rocket up unless we have fuel. And of course, the fuel is burned up in the process. So we are going to identify the inner function. The inner function's derivative must be present, but then it's going to disappear. If that was totally confusing, it will get a little clearer as we work through our first few examples. But let me keep reading here. Big section, we're going to use pattern recognition to find indefinite integrals. We will also see how to do a change of variables to find an indefinite integral. This will lead us to the general power rule for integration to find indefinite integrals. We will use a change of variables for definite integrals as opposed to indefinite up here. And we will evaluate definite integrals involving even and odd functions. There's a really neat shortcut, especially for odd functions, that makes a definite integration a whole lot easier. But we are going to start with the basics, and we're going to start with pattern recognition. So in this section, we're going to study techniques to integrate composite functions. The discussion is split into two parts. First is pattern recognition, and then we'll look at changing the variables. Both techniques involve what will be called a U substitution. With pattern recognition, we perform the substitution just in our heads. With the change of variables, we will actually write out the substitution steps. The rule of substitution in integration is comparable to that of the chain rule in deriving, because we're going to undo the chain rule. So let's see what the book says here. We have y is equal to our function capital F of u. U is equal to g of x. So we could rewrite that f of u as f of g of x. It looks like a composite function. F is the outer, g of x is the inner. So it says here the chain rule states that if we want to derive f of g of x, first we derive the outer, that's f prime. G of x stays the same, but then the chain rule creates this little g prime of x. And from the definition of an antiderivative, it will then follow that. Here is our g of x, and g of x's derivative. G of x is the rocket, g prime is the rocket fuel. When we antiderive, this rocket fuel will be burned up. We will antiderive capital F prime to capital F of g of x. And then don't forget your plus c. These results are summarized in the following theorem. Theorem 4.15, anti-differentiation of a composite function. Let g be a function whose range is in the interval of I, and let f be a function that is continuous on the same interval. If g is a differentiable function on its domain, and f is an antiderivative of f on that same interval, then, notice all this notation. Let me make this a little bit bigger. So we are anti-deriving a composite. We've got the outer function f, we've got the inner function g, and also present is g's derivative g prime. This is our rocket fuel. When we anti-derive, that rocket fuel is going to get burned up. We will anti-derive f, in this case to capital F, and g of x, the inner function, did not change. And we've got our plus c in there. Now that would be more pattern recognition. If we're going to do the full-on U substitution, we are going to let U equal g of x. So f of g of x can be written as f of u. And the dx is out, and now it is du. So when we anti-derive this f of u du, the rocket fuel, will disappear. F of u anti-derives to capital F of u plus c. So here, note we got outer and inner functions. Our outer function is the first one here after the integration symbol. F of g of x is our inside function, and then g prime is also present, the derivative of that inside function. So again, we're going to launch our rocket. This g prime and the dx get burned up in the process. That's the rocket fuel. We anti-derive f to capital F, and our inner function g of x stays the same. Don't forget your plus c. And I see an arrow in the corner. The statement of Theorem 4.15 does not tell you how to distinguish between f of g of x and g prime in that integrand. As you become more experienced at integration, your skill in doing so will increase. Of course, part of the key is familiarity with derivatives. The better we know derivatives, the easier it is to reverse the process. So here, our first example, example 1. It says recognize the pattern f of g of x times g prime. Let me blow this up a little bit. So first, we have to figure out what might be our inside function. Usually, if you see a set of parentheses to some exponent, what is in the parenthesis is your inner function. If you have a trig function like sine of something, usually what is in here is your inner function. Sometimes, if it's sine cubed and we move the cubed outside these brackets, then maybe the entire thing is your inside function. So let's see here. I see a set of parentheses, quantity squared. So let's say I'm going to assume, and let me even go to the notation again. So we've got f of g of x. So if I take what is inside the parenthesis and say, well, this might be my g of x, what is the derivative of what's inside? The derivative of x squared plus 1 is 2x. There it is. That's the g prime. So this, it's all ready to go. We don't have to do anything to sort of tweak it to get ready. This rocket is ready for launch. So what we're going to do, this in the parenthesis is our rocket. This is what we're going to anti-derive. It is a quantity to the second power. So to anti-derive that, we're going to have the same thing in the parenthesis, but remember the anti-deriving rule, we are going to raise the power by 1. We are going to divide by the new power 3. The g prime of x and the dx, this all is the rocket fuel. So when the rocket launches, this gets burned up in the process. And don't forget your plus c. Okay, now the first time you do these, you might be a little concerned. Did I get it right? Is my answer correct? We can always check by deriving. So I'm going to move this 3 out here and make it a 1/3. 1/3. Let's derive this with the chain rule and see if we get back to where we started. So the exponent would come down. 3 times 1/3 is 3/3, or just 1. I'm going to have the exact same quantity, but now I'm going to drop the power by 1 squared. And then the inner function's derivative to satisfy the chain rule. The derivative of x squared plus 1 is 2x. And the constant, whatever it is going to derive away. Notice that this answer is exactly where we started. X squared plus 1 quantity squared times 2x. Oop, I forgot dx on there. All right, so our anti-deriving was correct. We derived and got back to where we started. Again, take a guess. What is your inner function g of x? Hopefully its derivative is right there. G prime is ready to go. Our rocket and the rocket fuel is ready for launch. Okay, example 2. They've changed this one in the new edition of the book, but it's still just we're recognizing that pattern. So if you see e to some exponent, I'm just going to use u, e to the u, look, the u up here, this exponent is more than likely your inner function. So I'm going to blow this up a little bit more here. There we go. So if this 5x is our inside function, what is the derivative of 5x? Well, the derivative of 5x is 5, and the 5 is present. We've also got our dx. This rocket is ready for launch. I'm going to sort of rewrite it like this, though. E to the 5x, that's our rocket, and I'm just going to put this 5 over here with the dx. 5 times dx. So again, here is our inner function. Our u, what's the derivative of 5x? It's 5. So our rocket is ready for launch. Let me get myself a little more space here. So e to the something is its own derivative. It's its own antiderivative. So our antiderivative will have e to the 5x in it. And then this is our rocket fuel. It got burned up. And we're not going to forget our plus c. Now let's see if we derive this. We should get back to where we started. So what is the derivative of e to the 5x? Well, that's e to the 5x. But since that's more than x, we got to satisfy the chain rule. What is the derivative of 5x? Well, that's 5. And then the constant, no matter what it is, will derive away. So we are back to where we started. So that is the correct answer, 5e to the 5x. Now, I'm looking in my old notes. Let me throw another one in here. That was example 2. And this won't be in your notes, but maybe you have a little room to write it off to the side. Call this example 2.1. I just want to throw a trig function 1 in here. So I want to anti-derive 5 cosines of 5x dx. Okay, so we got to identify the inner function. You usually look for stuff in grouping symbols. Here I see the cos of a group. Oops, that was supposed to be, there we go, black ink. So if this is our inner function, what's the derivative of 5x? Derivative of 5x is 5. So our rocket fuel here, or excuse me, our rocket is the cos of 5x. Our rocket fuel is the 5 and the dx. So we launch our rocket. What is the antiderivative of cos? Well, that's going to be sine. Sine of what? The same 5x. The 5 and the dx, that's the rocket fuel, so it gets burned up when we launch, and we're not going to forget our plus c. So let's see if this is what we think is our answer. Let's derive it to see if we get back to the original problem. So what's the derivative of sine? Well, that's cos of the exact same quantity 5x, but we need to satisfy the chain rule. The derivative of 5x is 5, and the constant derives away to nothing. And that's where this problem began. So we have the correct answer. What's this? The integrands in those first two examples, they fit the pattern exactly. We only had to recognize that the pattern was there. We can extend this technique considerably if we recognize the constant multiple rule. So here is k times f of x. Well, remember, a constant, as long as it's multiplied, we can sort of factor it out in front of that integral symbol. We saw it with derivatives and summations, so here it is again. Many integrands contain the essential part, the variable part of our G prime, our rocket fuel, but they are missing a constant multiple. In such cases, we can multiply and divide by the necessary constant multiple as we are about to see. Let me make this a little bit bigger, and I'm going to copy the problem down so I can scribble around on it a little bit better. We are going to antiderive x times quantity x squared plus 1, quantity squared, dx. Okay, if we start looking at this for an inner function and its derivative, usually we can always try these parentheses. Let's assume that what is inside our parenthesis is g of x. So what would g prime of x be? Well, what's the derivative of x squared plus 1? It's 2x. dx. Do we have a 2x dx? We have the dx. We have the important part, the x. What are we missing? Let me move this over. We're missing the 2. So what I can do is multiply here by a 2 as long as I balance it with the fraction out front. What's the reverse of 2? 1/2. So what we did in essence here, we're multiplying by 1. We're multiplying outside the integral by 1/2. We're multiplying inside the integral by 2. If I factor this 2 out, 2/2 is equal to 1. So what we're doing here is not really changing the problem. It's just looking a little different. And now, if you notice, we have our rocket fuel. We have the 2x and the dx that are necessary to launch. 2x dx is our g prime. It was not there completely, but we just had to tweak it with a constant. We put a 2 inside. We put the reciprocal outside, 1/2. So let's see. We've got to bring this 1/2 along for the ride. And it's time to launch the rocket. So we have this quantity to the second. Well, we're going to raise that quantity, x squared plus 1. Now it's up to cubed. We are going to divide by that new exponent, 3, and don't forget your plus c. The 2x and the dx are the rocket fuel that got burned up on launch. And there's one more thing we can do to make this look a little prettier. Remember, math should not be correct. It should also be aesthetically pleasing. It should be nice to look at. So what we could do here is either multiply the 2 by the 3 and put a 6 down here, or we could pull that 3 out with the 2 and just make this fraction 1/6. And then we'll have x squared plus 1 to the 3rd power plus c. Now, if you want, we can derive this to see if we get back to the original problem. All right, well, let's derive, and of course, we're going to use the chain rule. So, deriving, we first bring the exponent down and multiply. 3 times 1/6 is 3/6, or 1/2. And then this quantity does not change. We derive around the inner function. The exponent does drop 1 power. And now we need to satisfy the chain rule. So the inner function here, x squared plus 1, what is the derivative of that? 2x. The constant, as always, will derive away to nothing. So we're real close to the original setup to the problem. If we just multiply 2x times a half, that becomes 1x. And that's exactly how this problem started. X outside and then x squared plus 1 squared in the parenthesis. We found a good solution. Now I see this down here. What's this? Ooh, be sure you see that the constant multiple rule only applies to constants. We cannot multiply and divide by a variable and then move the variable outside the integral sign. For instance, here's x squared plus 1 quantity squared. We're missing the inner derivative altogether, 2x, so we cannot put a 2x here and a 1 over 2x outside. That is highly illegal. After all, if it were legitimate to move variable quantities outside the integral sign, you could just move the entire integrand out and simplify the whole process. The result would be wrong every time, but it would be much simpler. Okay, now this leads us from pattern recognition to an actual changing of the variables. With a formal change of variables, you completely rewrite the integral in terms of u's and du's, or any other convenient variable. Although this procedure can involve more written steps than pattern recognition, it's useful for the more complicated integrands. The change of variables technique uses Leibniz notation for the differential. That is, if u is g of x, then the derivative of u, du, would be g prime x dx. Because remember, if we derive u, it would be du dx would be g prime, and then we move the dx over to the other side. And then the integrand, or the integral in Theorem 415, will take this form. So here is our f of g of x. Well, we're going to let u replace g of x, so that becomes f of u. The g prime of x and the dx all together gets replaced by the du. So then when we anti-derive, everything is now in terms of u. This just becomes capital F of u plus c. If you're a little confused, sometimes it gets clearer when we actually work out a problem. So let me get my, here we go, the integral of, or the antiderivative of. Now I'm going to rewrite this as a half power because we are going to get rid of the radical at some point. So that is 2x minus 1 to the half dx. So let's see here. We are going to come up with a u substitution. We are going to let u equal 2x minus 1. So if we derive that du dx, the derivative of u with respect to x would just be a 2. Now we want to get the du by itself, so we're going to multiply both sides by the dx. So du is 2 dx. And let me get rid of a little bit of this so I have some more room. So let's take what they gave us, the stuff here in black ink, and rewrite it using our substitution. So this 2x minus 1 is out. That is replaced with a u. So that becomes u to the 1/2. Now notice, for our rocket fuel, we need a 2 dx. We've only got the dx. So we could, if we need to, put a 2 here, as long as we balance the 2 inside with a 1/2 outside. So this 1/2 is going to come down to this part. And now this, the 2 and the dx, 2 dx, can be just replaced with a du. du. All right. We are now ready to anti-derive. So we've got the 1/2. That's going to come along for the ride. And now we've got u anti-derived with respect to u, or excuse me, u to the half anti-derived with respect to u. So we anti-derive u to 1 power higher, 3/2. We would divide that u by 3/2, or bring up and flip, multiply by the reciprocal 2/3. 2/3 u to the 3/2 plus c. Now if you leave the plus c in the brackets, and actually let's do it like that. Put it in there. Okay. Now we're ready to, let's distribute the 1/2, and then we'll take our u out and replace it with what we originally subbed in there. So if I distribute the 1/2 to the 2/3, I'll get 2/6, or if you catch, we can reduce on the diagonal. That will reduce down to 1/3 u to the 3/2, but we're going to take out the u, because remember at the start of the problem we let u equal what was under the radical. So let's put that 2x minus 1 back in there. And then if we do distribute the 1/2 to the unknown arbitrary constant c, half of an unknown c is just another c. So there we go. 1/3 quantity 2x minus 1 to the 3/2 power plus c. If you think you may have made a mistake and your deriving is better than your integrating, we can always check by differentiation. So if I was going to derive this, we would first bring down the exponent and multiply. 1 over 3 times 3 over 2 is 3 over 6, or 1/2. And then we have this quantity. Now to 1 power lower, 3/2 minus 2/2 is 1/2. And then the constant derives away to nothing. And I almost forgot the chain rule. This inner function would need derived. 2x minus 1 derives to a 2. That 2 is going to hit the 1/2 at the front. Half of 2 is 1. So this is 2x minus 1 to the 1/2 power, and that's where this problem all started. So we figure out our inner function, replace it with a u, anti-derive, and then we switch back at the end. All right, this is a biggie. This is example number 5. In the exercises at the end of this section, there's a special part. It says solve the problems, the following problems with the same technique as example 5. So in class, I will call this an example 5u sub, and there will definitely be one of these on the test. So this is very similar to the last one. Anti-derive radical 2x minus 1. This is anti-derive radical 2x minus 1, but we have a times x here. So it's going to be kind of similar to the last one, but there is a definite twist to this one. So let's start it like we did the last one. We are going to let u equal 2x minus 1. If I derive that, du dx would be 2. And then I would multiply both sides by the x, so I've got a 2 dx over here. So let's go back over to our original problem and do our substitution so far. So this, under the radical, is our u, so that again is going to be u to the 1/2, just like we did before. We do need a 2 dx, and we don't have a 2 dx, so I could squeeze a 2 in here as long as I balance it with the reciprocal out front. So now there's a 1/2 out there, just like we saw in the last example. So we've got a 1/2 out there, and then the 2 dx turns into a du. So as far as our substituting goes, we've substituted this out. We've gotten rid of the dx, but we've still got this x. I'm going to put it here in red ink because that is our last troublemaker. We have so far turned everything into terms of u. We have a u to the 1/2, we have a du. This is our last x, and we're kind of stuck on how to get rid of it. We want everything in terms of u. So remember, we've already defined u in terms of x. So I'm going to bring this down here for a little scratch work. U is equal to 2x minus 1. Let's solve that for x. So first thing, add 1 to both sides. U plus 1 is equal to 2x. And then if we divide by 2, x is equal to u plus 1 all over 2. So this x over here I have in red, that is out. We're going to replace it by this quantity here I'm boxing off in blue, u plus 1 over 2. So let's see what this is going to look like in its final form. 1/2 antiderivative of the red x is out. Now that is u plus 1 over 2. We've still got this u to the 1/2, u to the 1/2, and then I've got my du. So I guess I got to erase this and put in my du. Now everything is in terms of u's, and we have a du at the end of it all. Now, it's still not ready to anti-derive. We are going to clean some more stuff up, make it a little nicer to work with. The first thing I notice, we have this denominator 2, which is multiplied in here. So let's just drag that out front. So now this becomes a 1/4. Antiderivative of u plus 1 times u to the half du. And we're almost ready to anti-derive, just a little more algebra. Let's distribute u to the half power here and here. So we've got a 1/4 antiderivative of. This is u to the first times u to the half. We add exponents when we multiply like bases. So that's u to the 3/2 plus u to the half times 1 is just u to the half. That's an ugly 2. That's a little better. And then du. Okay, a lot of work to set this up. We have yet to do any calculus, but here it comes. So we've got our 1/4. And now let's antiderive u to the 3/2. That is going to be u to 1 power higher. 3/2 plus 2/2 is 5/2. We will divide that by 5/2 or multiply by the reciprocal 2/5. Plus u to the 1/2. Raise the power by 1. U to the 3/2. We could divide by 3/2 or multiply by the reciprocal 2/3. And then we have plus c. Whoa. Oops. Okay, I'm going to move this up. Now, remember our original u was equal to 2x minus 1. So we're about the point we are going to take the u's out and replace them with 2x minus 1. We are also going to distribute this 1/4. 1/4 times 2/5 is 2/20, or that's 1/10. U to the 5/2, that's a terrible 2. There we go. Plus, we're going to distribute the 1/4 here. So that would be what? 2/12, or 1/6. U to the 3/2 plus 1/4 times an unknown arbitrary constant is just another unknown constant. Now I did leave the parenthesis empty where the u's used to be because now goes in there 2x minus 1, our original substitution. Now we could derive that to check to see if we get back to where we started, but I really don't feel like doing that in the video. I have the utmost confidence that that is the correct answer. So again, remember that is what I call an example 5 U sub. They have a special spot in the exercises. There will be one on the test that says solve this using the method of example 5. Okay. Another change of variables. This one has some trig functions in it. Ooh, now this one's interesting. And I'm going to rewrite it down here for this reason. I've got this sine squared of 3x. Now, my first thought would be to check 3x for the inner function, but if we derive 3x, we just get a 3, and we've got this whole other cos out here. So another option is, since this is sine squared, I could put the squared here right on the sine, or put it outside these brackets. And now I'm going to change ink color. So here is a cos of 3x, and we have a dx. All right. So we tried 3x as the inner function, and it didn't work because of this cos. What if we let u equal everything in those black brackets? What if we let u equal the sine of 3x? Well, the derivative of u would be du dx. And what's the derivative of sine 3x? Well, that's going to be cos of the same 3x, and then we need the chain rule. Inner function is 3x, derivative of 3x is 3. And then to get du by itself, I will move my dx to the other side. So there we go. We've got our u is equal to sine 3x. That all underlined in blue. And if we have a 3 cos 3x dx, we can replace that with a du. We've got the cos of 3x and the dx part, so all we're missing is that 3. So if I squeeze, I guess, anywhere in here, I could put the 3 right here or next to the dx. It doesn't really matter. But if we put a 3 inside the integral sign, we must balance it with the reciprocal 1/3 out front. So let's write this all now in terms of u's. So we have 1/3 antiderivative of, this is now not sine of 3x squared, it is now just u squared. And then all of this, the 3 cos of 3x and the dx, all of that turns into a little old du. Okay. And I'm going to get rid of this. I don't want to get rid of my original sub because we're going to need that at the end. I'll do this. There we go. So now it looks like it's going to be a lot easier to antiderive. How do we antiderive something to the second power? Well, we raise the power by 1, we divide by the new power, and we don't forget our constant. So if we multiply the 1/3 by the u cubed over 3, that's going to be u cubed over 9 plus c. So for our last step, let's take out the u and replace it with our original substitution. So this is going to be not u cubed, but something cubed over 9 plus c. And let's put our sub back in there. U is out. Sine of 3x is back in. So 1/9 the sine of 3x, quantity cubed, plus our unknown constant. Very nice. Okay, here they give the guidelines for making a change of variables. Step 1, choose a substitution, what you think is the inner function. Usually it's best to choose the inner part of a composite, such as a quantity raised to a power. Next, find your du. It's going to be g prime of x dx. Rewrite the integral in terms of the variable u. Find the resulting integral in terms of u. And then replace the u with the g of x to get your antiderivative back in the terms of x. And of course, we can check our answer by differentiation. So far, we have seen 2 techniques to applying a substitution. You'll see more techniques in the remainder of the section. Each technique differs slightly from the others. You should remember, however, that the goal is the same with each. You're trying to find the antiderivative of an integrand. So now what we've been working on is going to lead us to a more powerful power rule. Remember when we were anti-deriving x to the nth, it became x to the n plus 1 divided by n plus 1. 1 plus c. We raised the power by 1 divided by the new power. That was our regular old power rule. Now it's going to get a little more powerful. One of the most common types of u subs involves quantities in the integrand that are raised to some power. Because of the importance of this type of substitution, it's given its own special name, the general power rule for integration. A proof for this rule follows nicely from the simple power rule together with Theorem 4.15. So get ready for a bunch of notation. Here it comes. We are anti-deriving some function g of x to the nth power, and its derivative g prime is present with the dx. So our rocket fuel is going to burn up, and our antiderivative is that g of x to now n plus 1 power over n plus 1 plus c. And this is true as long as n is not equal to -1, because n would be dividing by 0, and that's not very nice. The one below, they just do it with a u substitution with all the variables fully subbed in there. So this g of x to the nth power is now u to the n. The entire g prime of x dx, that's been all replaced with this little old du. So when we antiderive that, u to the n plus 1 in the numerator, raise the power by 1, divide by the new power, n plus 1. Don't forget your constant. We're good as long as n is not -1. So there is our more powerful power rule. Let's try it out. So Letter A, antiderive 3 times the quantity 3x minus 1 to the fourth power dx. So this one, let's just look for the pattern recognition. I'm going to assume this is my inner function. What is the derivative of 3 or 3x? Well, that would be 3 dx. So we have the 3, we have the dx, that is our rocket fuel. When we launch our rocket, the rocket fuel burns up, and then our rocket goes up. So here's our rocket in the parenthesis. It goes up a power, and we divide by the new power. And don't you ever forget that plus c. Now, of course, you know this divide by 5. If you're not a fan of that, you could drag it out there and write it as 1/5 that quantity to the fifth power plus c. Whatever floats your boat. Letter B. Ooh, now look at this one. We got some quantities in parenthesis. Ooh. So one of the sets of parentheses is going to be our inner function. The other one will be the inner function's derivative. So let's say here, let's assume, okay, maybe this is the inner function. What do I get if I derive this? E to the x derives to e to the x, but 1 would derive away to nothing. So maybe I got it backwards. If we go this way, what is the derivative of this? Well, e to the x derives to e to the x. This x derives to a 1. So we've figured out that we do have an inner function and that inner function's derivative. So this is our u. This is our u prime. And we also have our dx there. So the rocket fuel is just going to disappear. You know, when we launch, u prime is gone. The dx is gone. Now there is an implied exponent here. That is e to the x plus x quantity to the first power. So we are going to raise that same quantity up now to the second power, and we're going to divide by that new power, and we're going to put on our plus c. And there we go. If you're not sure that answer is right, you can check by deriving, and that's an easy enough check. I'm just going to make my divide by 2 into a 1/2 out here, and if we derive, we would bring down the exponent and multiply. 2 times a half is 1. We would have this same quantity now to the first power, and then for the chain rule, we would derive that as a quantity to e to the x plus 1. The constant derives away. So we got a good answer. Letter C. Ooh, look at that. Now I'm going to rewrite this. I always like to make my radicals as half powers. So I'm going to put it here at the front. X cubed minus 2 to the half. And then we've got a 3x squared. So this looks like it'll just be a nice pattern recognition. I am going to assume that my inside the parenthesis is my inner function. What is the derivative of the stuff inside the parenthesis? Well, that's 3x squared. And I forgot my dx. Please forgive me. So this, what the 3x squared and the dx, that is our rocket fuel. That's going to burn up. Because if this is our u, the derivative of that would be u prime, 3x squared dx. So the rocket launches, and this stuff burns up in the process. So our rocket, x cubed minus 2, is going to go up a power from 1/2 to 3/2. That's a 3. And we're going to divide by 3/2 or multiply by the reciprocal 2/3. And we're not going to forget our constant. So 2/3 times that quantity to the 3/2 plus c. Letter D. Let me get some of these out of here. There we go. Ooh. Now we've got a rational expression. Denominator is in parenthesis raised to the power 2. I'm guessing that's going to be the inside function. First, let's bring that denominator up and give it a negative exponent. So our numerator is negative 4x, and then our denominator comes up. 1 minus 2x squared, but now it's going to be to the negative 2 since we brought it up from the denominator. All right, I'll go out on a limb and assume that what is in these parentheses is my inner function u or g or whatever you want to call it. What would be the derivative of the stuff in the parentheses? Well, the 1 would derive away, and this would be a negative 4x to the first, and holy cow, there it is. There's our u prime. And of course, remember the dx is part of the rocket fuel. So anti-deriving, we are all ready to go. We launch our rocket. this fuel burns up and our rocket goes up. 1 minus 2x squared is now up to the negative 1 power, and we are going to divide by negative 1. And we're not going to forget our constant plus c. So let's see now. Of course, negative exponents are bad manners in math class, so we do want to get rid of that negative exponent. Now keep in mind there is an implied 1 out here, so when this moves downstairs because of the negative exponent, we will still have a 1 up there in that numerator. So we got a 1 up here, and this negative, we can put that anywhere in the fraction. I'm just going to put it more over here. And then our quantity moves downstairs. 1 minus 2x squared is now in the denominator. It would be to the first power. And of course, you don't have to put the 1 there. That's implied. And then I'm going to tack on my plus c. So negative 1 over that quantity plus c. And I see one more down there, letter E. Okay. All right, so we've got a cos squared and a sine. Okay, now when I see the trig function like that cos squared, I at least think about it mentally like this. That is cos of x quantity squared. We could put the squared out as long as it's not just on the x, as long as they're squaring the quantity, we will be fine. And I'll put my sine of x dx here. So I'm going to again assume that what is in the grouping symbols is my inner function. What is the derivative of cos? Well, cos derives to negative sine. So we're missing a negative. So if I put a negative 1 here, or a negative 1 over 1, the reciprocal of that would be negative 1 over 1 out here. So what I've kind of done is, and don't think that's we're subtracting, that's multiplication there. So we multiplied inside by a negative 1, outside by a negative 1. What we've actually done is multiplied by 1, so nothing is going to change. So our inner function is cos x. Its derivative is present. That's our rocket fuel. That's going to burn up when we launch. So now we're going to have, don't forget this negative outside the integral symbol. We've got negative. Now this is going to be cos of x, but we raise the power to 3, and we divide by 3. And we don't forget our plus c. Negative 1/3 cos cubed of x, or cos cubed of x plus c. Now I'm looking in my notes, and I have a couple others in here that I don't see on the slideshow. I might have added them in years past. Now hold on. Oh yeah, okay, no. Just one more here, one more. I'm going to get this out of the way. Yeah, the book changed a couple things, and I'm looking in my old notes. I'm going to call this letter F, antiderivative of e to the 3x squared times 2x. And I don't like that exponent. Let me just back that up. X squared times 2x. All right, now this one, I'm going to assume that e's exponent is my inside function. So 3x squared, I need its derivative to be present. The derivative of 3x squared would be 6x. So we've got a 2, but we want that to be a 6. Now the book might kind of show a confusing way to do this. I'm going to do it like this. I like to do it piece by piece. Usually students prefer this method a lot more than the other one you see in the book. So right now, this 2 is kind of causing us trouble. We don't need it, so I'm going to move the 2 out front. So the 2 is now out here. And again, we want this function's derivative. We want a 6x to the first. So I'm going to put the 6 I need here, but we're going to balance it with a 1/6 out front. So now out here, we've got 2 times 1/6, or 2/6, or 1/3. The antiderivative of e to the 3x squared times 6x dx. I forgot my dx. So we are ready to launch our rocket. Oops, get over there. We go. So remember, this is our inner function, e to the 3x squared. 3x squared is inner. Derivative of that is 6x dx. So this is our rocket fuel that burns up. It's gone. The 1/3 is a constant, so it comes along for the ride. And e to something is its own antiderivative. E to the 3x squared power plus c. So 1/3, yeah, there we go. A good antiderivative. What's next? Okay, a formal change of variables for definite integrals. Remember, all the ones we've done up until now have been indefinite. They have been families of functions. We have added a plus c at the end. But it says when using a u sub for a definite integral, it's often convenient to determine the limits of integration for the variable u rather than converting back to the variable x to evaluate the original limits. This change of variables is stated explicitly in the next theorem. The proof is combined with the fundamental theorem. And the examples we've done before this, it was always an indefinite integral. We let u equal some stuff. We anti-derived, and then we put that stuff back in for u. Of course, we can anti-derive a definite integral or do a definite integral the exact same way, but sometimes it's easier to convert to u's and never convert back. So here, this is going to be f of u times du. But look what they did with the limits. B is no longer the upper limit. Now it is g of b. We run that upper limit through the g function. Lower limit a is no longer a. Now it is g of a. So when we do this technique, we convert to u's and we never ever convert back. We change our limits so we can evaluate without changing back. So here we go. Evaluate this definite integral, 0 to 1 of x times quantity x squared plus 1 cubed dx. So let's set this up. Actually, I'm just going to copy it down here so I can move stuff around and write on it. 0 to 1 x squared plus 1 to the 3rd power dx. I can move this over here, and I got a little more room. So we are going to let u equal x squared plus 1. So then du dx would equal 2x. The 1 would derive away, and I would move my dx to the other side. So what we need is a 2x dx. We have the important part. We have the x. We have the dx, so we're missing a 2. So to tweak this, I can put a 2 where I need it, as long as I balance it with a 1/2 out front. So now let's see where we're at. We've got 1/2 definite integral from 0 to 1. This is our inner function u, so now that's just u to the 3rd, and the 2x and the dx together form the du. But let me even say these upper and lower limits are still in terms of x. In terms of the variable x. Everything here is in u's. We could anti-derive and then change back with our u substitution and evaluate the 0 and the 1. Or if we don't feel like converting back into x's, we are going to convert our upper and lower limits into new limits in terms of u. So we're going to change those upper and lower limits to in terms of u, and I erased what my original u sub was, x squared plus 1. So we let u equal x squared plus 1. So I'm going to take the old upper limit of 1 and I'm going to plug it in for x. So 1 squared plus 1 is 2. My new upper limit is 2. If I take my old limit of 0 and plug it in for x, 0 squared plus 1 is 1. Now my upper and lower limits are in terms of u's. So we can convert or we can anti-derive and evaluate without ever switching back. So we've got our 1/2. The antiderivative of something cubed is that same something to the 4th over the new exponent 4. We remember no plus c because this is a definite integral, and we will evaluate that from 1 to 2. Again, if we wanted to take this u out and put back in the x squared plus 1, we could evaluate the old limits. But we're not switching back. We're going to stick with u's, and we will evaluate here. Ooh, and before we go any farther, I would pull this denominator 4 out with this 2 and make that 1/8 u to the 4th from 1 to 2. So as the fundamental theorem says, the upper limit jumps in first. 2 to the 4th is 16. Oop, get back there. 16. Minus lower limit jumps in. 1 to the 4th is 1. So that becomes 16 minus 1 is 15, 15/8. 15/8. There we go. What's this? That was the original problem. They do the graphical solution here too. Let's see what that would look like. So the graphing utility, we could graph our function. It's going to look like this, parabolic shaped up, because it would be an x to the 4th, or no, 6. What would that be? X to the 6th, x to the 7th. Yeah, so in the first quadrant, we are going to be going up. And then we could use an integral feature to find that shaded region, 1.875, which is our fraction. What was it? 15/8. So notice in example 8, we would attain the same result when we rewrite the antiderivative, 1/2 u to the 4th over 4, in terms of x and evaluate the definite integral with the original limits. So here is where we did our u sub. And if we put our u back in, x squared plus 1, we would evaluate the old limits. So the 1 would jump in, the 0 would jump in, we'd do our computations, we'd get the exact same answer, 15/8. Sometimes it's just easier to convert to u's and never convert back. Example 9. We've got another definite integral here. Let's see what happens with this one. I'm going to move this up here, and naturally I'm going to bring that radical from the denominator up, and I'm going to make it a negative half power. So denominator comes up, 2x minus 1. Now it is to the negative a half, and I'm going to put my dx on there. So let's start thinking u substitution. So u might be the 2x minus 1 in the parenthesis, 2x minus 1. And if I derive that, du dx would equal 2. And then I'd move the dx to the other side by multiplying it over there. So we've got a u, we've got a du. Do we have a 2dx? Well, we've got the dx, so I could squeeze a 2 in there as long as I balance it with a 1/2 out front. So let's start doing our conversion. We've got our 1/2. I'm going to put my definite integral symbol there. I'm not going to bring my limits, though, because we are going to convert the 1 and the 5 into new limits. But this is going to be u to the negative a half, u to the negative a half. The 2dx can be replaced with a du, but now we've got a troublemaker. Oop, I wanted to switch to red ink. X. We've got this x. This is kind of like example 5, similar to that example 5 u substitution. And before we worry about that, let's convert our limits over to new limits. Let's find a new top and bottom number. So I'm going to take this old top number 5, and I'm going to plug it into my u over here, 2x minus 1. 2 times 5 is 10, minus 1 is 9. Now I just noticed I'm doing this problem fairly different than I've done it in the past before, but let's keep moving on and let's see if this works out this other way. If not, you'll never know because I will just delete this part of the video and re-record it. But again, let's put that 5 into our u. 2 times 5 is 10, minus 1 is 9, so maybe my new upper limit is 9. And if I put the 1 in there, 2 times 1 is 2, minus 1 is 1. So our lower limit didn't change, but our upper limit did. Now we've got to take care of that troublemaker x right here. So again, we're going to go back to our u sub. U is equal to 2x minus 1. u equals 2x minus 1. Let's solve that for x. So add 1 to both sides, and then to get x alone, we will divide by 2. So x is equal to u plus 1 over 2. So I'm going to take out this red x and replace it with u plus 1 over 2. And I think I'll just clear a little room up here so I can move this up and do that. There we go. So we've got 1/2 definite integral 1 to 9 of u plus 1 all over 2, which replaces the red x, and then this is u to the negative 1/2 and a du. Okay, I hope this works out. So very similar to the one we did in example 5. This is all multiplied, so this 2 denominator can be dragged out front, where it'll hit this other half. Half times a half is 1/4. And then we've got our definite integral from 1 to 9. And now we've got, in a grouping symbol, a u plus 1. And then out there we've got a u to the negative 1/2 du. Okay. Before we anti-derive, of course, we're going to distribute the u to the negative 1/2 that's outside in here, and we will add the exponents as we go. So this is now 1/4 from 1 to 9. When we distribute, we would add the exponents, 1 plus a negative 1/2. That'll be u to the 1/2, plus this will just be u to the negative 1/2 du. Okay, we've done a lot of work, and now we are finally ready to do a little calculus and anti-derive. So again, the 1/4, that is a multiple that will come along for the ride. U to the 1/2, we're going to raise that power up to the 3/2 and divide by 3/2, which is the same as multiplying by 2/3. Plus u to the negative 1/2, we're going to raise that up to the positive 1/2 and divide by 1/2, which we can bring up, flip, and multiply by 2. Again, no plus c is required because we are doing a definite integral, and then my limits are 1 to 9. Okay, now to actually evaluate this, I'm going to take out the exponents, the 3/2 and the 1/2, and let's put those back into radical form, because it's easier to see what we're doing when we plug in numbers. So here we've got a 2/3, and then u to the 3/2 is going to be u, the square root of u, to the 3rd power. And then here we're going to have 2. U is under the radical, and that will be the square root of u to the 1st. Oop, and I forgot, we're going to go 1 to 9 on that, 1 to 9. Now, a little exponent trick you might have forgotten since an algebra class. This square root of u cubed, I could do that as the square root of u quantity, square root the u first, and then cube that answer. That might make it a little easier to evaluate this one without a calculator. So I should shrink this up just a little bit. There we go. So let's see. The 9 is going to jump in first, so I'm going to put this 1/4 way out here, and then we'll do all our fundamental theorem inside. So we've got this 2/3, and then the 9 is going to jump in. The square root of 9 is 3, and then that 3 to the 3rd power is 27. And then the 9 is going to jump in here, plus 2. The square root of 9 is just 3. So that's 2 times 3. I'm just going to write it as a 6. So there is our upper limit evaluated. Let me clear these out. And now it's time to do the lower limit. So the fundamental theorem says we always subtract. This will also be as a quantity. The 1 jumps in here. The square root of 1 is 1. 1 cubed is 1. Times 2/3 is 2/3. And then the 1 jumps in here. Square root of 1 is 1. Times 2 is 2 plus 2. So the calculus is over. From here on out, it's just arithmetic. And there's plenty of chances to make silly little mistakes in arithmetic. So let's see here. That 27 over 1, we can reduce on the diagonal. That'll be 2 times 9, or 18, plus 6, minus 2/3, distribute the negative, minus 2, and this is all got a 1/4 out front. So let's just work with those whole numbers first. 18 plus 6 is 24. 24 minus 2 is 22 minus 2/3. And we're going to multiply that by a 1/4. Let's see, 22 minus 2/3. That would be 21 1/3 with a 1/4 out front. Oh, I hope this worked. And I'm going to turn that 21/3 into an improper fraction. So let's see, 3 times 21, that's 63, plus 1 more. 63 plus 1 is 64 over 3 times 1/4. And if we just multiply straight across, we'll have a 12 in our denominator. 64/12. Now to reduce that down, the first thing I notice is that they're even numbers, so I would just mentally cut them in half. Half the numerator is 32, half the denominator would be 6. They're both even again, so let's chop them in half again. Half of the 32 is 16, half of the denominator is 3. Hallelujah, that is the exact answer I've got in years past when I did a different method. I can't believe I kind of screwed that up from the get-go, but it did all work out in the end. The method we were supposed to do, and I dragged my problem off of there, another way to do this, it was x over root 2x minus 1. An alternate way would be to let u equal the entire denominator, radical and all. So we would let u equal 2x minus 1 to the half power. And then we can continue with the problem like that. It's pretty much the same cut and dry. We would have different upper and lower limits, but our final answer would be 16/3. If you're really curious to see that happen, go back to my old calculus video on the old playlist. That would make this video 5-5. 5-5, integration by substitution. You could just fast forward to example 9. So there is another way to do this. Okay, moving on. I think we're almost done. Ooh, now this is so interesting, I think. Geometrically, we could interpret the equations from that last example. Remember, what we're doing here is finding sort of area under a curve. Here's our original equation, all in terms of x's. If we were to graph that, the graph would look like this. We're going from 1 to 5 on the x. That x over the radical, it's almost a straight line, but what we found would be this area if we left everything in terms of x. The other way to do the u sub, it would look like this. U squared plus 1 over 2. Well, if we graphed that, it would look like this over here, the blue area I shaded in. Because we converted and never converted back, the area here under this line, highlighted in black ink, is the exact same as the area over here, highlighted in blue ink. So nothing got changed. We changed the function and how it looks, but the area under it would stay constant. Beautiful, beautiful mathematics. Okay, now we're getting real close to the end here. Even and odd functions. It says here, even with a change of variables, integration can be difficult. Occasionally, we can simplify the evaluation of a definite integral over an interval that is symmetric about the y-axis or about the origin, and by recognizing the integrand to be either an even or an odd function. So here, this theorem has sort of like two, I guess you could call it, shortcuts. So if, well, let's say, f is an integrable function on the closed interval from negative a to a. Notice those are the same numbers, one positive, one negative. That has to be the case for this to work. That's usually the dead giveaway on the AP test that one of these might apply. Your upper and lower limits are a positive and negative of the same number. So if it's even, and let's do a quick review here. Remember, even functions are symmetric around the y-axis, like if we have a parabola opening up. So if we're going from negative a to a, and I'm going to do a parabola opening down. So like this. So here would be negative a, here would be positive a. If we want to find all of this area under the curve, it might be easier to just find this area and then multiply by 2. So look at this integral here I'm circling in blue ink, the integral from negative a to a of f of x dx. They change it, they put a 2 out front and make the lower limit 0 and leave the upper limit alone of the same function. So because of the nature of even functions being symmetric around the y-axis, we can take this more complicated integral, get rid of the negative a at the bottom, change it to a 0, and just put a 2 out front, because we're going to again find this area and double it. Might make your computations much easier. The even better one is if you're dealing with an odd function. Remember, odd functions have origin symmetry. My favorite odd function would be x cubed. Would look something like this. There we go. And if I'm going, let's say here from negative 4, I would accumulate over here some what you could call air quote negative area. And over here on the other side, when we go to positive 4, we will accumulate area above the curve, or the x-axis, sort of positive area. These will be the exact same. Like this might be negative some amount. This will be the same positive. They will net out to 0. So if your function is odd, and you're sure it's odd, and your limits go from negative to positive of the same number, that function is just equal to 0. Again, you got to make sure that you are dealing with an odd function, or this might just blow up in your face. And that, okay, here, another little thing I just sort of created on my own. Remember for trig functions about even and odd. If we look at a basic sine graph from negative pi to pi, we can see there in the graph the origin symmetry. So sine of x is odd. And what that means is if we have the sine of negative pi, it's exactly the same as the negative of sine of pi. It's kind of like that negative can sort of be factored out if your function is odd. On the other hand, cos, think about cos around the y-axis. Remember, positive cos starts up here at a peak. So this around the y-axis kind of looks like a parabola opening down. So we are symmetric around the y-axis, so cos is even. And that means the cos of a negative value is the same thing as the cos of the same value but positive. It's kind of like that negative got eaten up by cos. With sine, the negative escaped. With cos, the negative was consumed. That will be helpful in determining even and odd functions like this. Now let's say you're on the AP test and the graph is not given. Evaluate this definite integral. As soon as I notice the upper and lower limits are the same, one positive, one negative, that would send off alarm bells in my head. So this could be an even or an odd function. We're not sure yet. What we've got here, sine of x quantity cubed, that's supposed to be a cubed. And then we've got times a cos x, and then plus sine x times cos x. So let's figure out if we've got an even or an odd here. And I guess it would be a good time, let's do another quick review here. The way I showed you to determine even and odd functions in pre-calc, let me just make a new slide. What we would do, they would start us with f of x is equal to something. I would come over here and find the negation, negative f of x. Over here, we would just distribute a negative. And then we would evaluate down below f of the negative of x. If it takes us back to the original, we're even. If it takes us to the negation, we're odd. If it doesn't take us to either of those, then it's neither, even, odd, or neither. So let's see what happens here. Oops. So I guess this is our f of x, f of x. We're going to find the negation of f of x. So just imagine we're going to distribute a negative across this, what I just underlined in blue. The first two terms are multiplied, so that would be a negative sine cubed x times cos x. Distribute the negative, that would now be a minus sine x cos x. So now to perform the test, we are going to perform f of negative x. So let's put negative x's in there. This is, back up to the original. That's going to be the sine cubed of negative x times the cos of negative x plus the sine of negative x times the cos, I'm running out of room, of negative x. And I erased all that good stuff I had there. But remember, just real quick, with sine, the negative escapes, because sine is odd. Sine of negative x is the same as the negative of sine x. And the cos of negative x is the same as the cos of x. So sines eat up negatives, or no, excuse me, sines let negative escape. Coses eat up the negative. It's like that negative got eaten by the letter C, and cos kind of looks like a Pac-Man. So sines let negatives escape. So let's go down here. This first term, that negative is going to escape. So now it's out front. Negative sine cubed of x. And remember, the cos is hungry. That negative gets eaten up. So this just stays the cos of x. Here we've got another sine of negative x. That negative will escape and turn this plus to a minus sine of x. And now we've got a cos of a negative, and that cos is hungry. It's going to eat that negative up. So now that's just a cos of x. So what I have down here in black ink, does it match the original function? Are we even? No, it doesn't match the original. Does it match the negation? Absolutely it does. So what we've just found out is the function we're dealing with is an odd function. So odd function. Exclamation point. Because the upper and lower limits are the same, positive, negative, half, pi, and our function here is definitely odd, that whole thing is just equal to 0. It's that easy. You know, that is this theorem here. Back. If we're odd function and our upper and lower limits are the same, positive, negative, that limit is equal to 0. Because this graph will have an equal number of area above and below the x-axis. If you're on the AP test and they happen to give you the graph, that should be a dead giveaway. We are going from negative half pi to 0. This would be negative some amount of area. From 0 to positive a half pi, that would be the same amount, but in the positive side, that is going to net out to 0. Now, one small complaint I have about this textbook, they give us this theorem, and they give us a great example for part 2 of it, but they give us nothing for the even part. So I created my own example. Y equals negative x squared plus 9, and that is from negative 3 to positive 3. We want to find that area. So if we wanted to set up the integral this way, it would be from negative 3 to 3 of our function, x squared plus 9 dx. Now granted, this is not a hard one to anti-derive. It would not be difficult to evaluate. But it would be easier if we recognize that this is an even function and our upper and lower limits are symmetrical about the y-axis, negative 3 to 3. So the theorem says what we can do is change our limits from not negative 3 to 3, but 0 to 3, as long as we put a 2 out here. And then the rest of it stays the same, negative x squared plus 9. Because, you know, you should be figuring out by now, lower limits of 0 are much nicer to evaluate. And you know, the original integral, we would find the area starting at negative 3, and we would find this area as we work our way to positive 3. We would collect all that area. What we're going to do is find the area from 0 to 2, or excuse me, 0 to 3, and just double it to account for the reflected half over there in quadrant 2. So I'm just going to get rid of all this. There we go. And let's evaluate our easier integral. So this 2, that's a constant multiple. That's going to stick around for a little bit. Let's anti-derive our first term, negative x to the third divided by our new exponent, plus 9 gets anti-derived, a variable gets attached, and we're going to go from 0 to 3. And let me move this up here so I have a little more room. Okay, so we've got our 2, and then the 3 jumps in. So 3 cubed is 27, and it is a minus 27 over 9 plus 3 jumps in here. 9 times 3 is 27. So there's our upper limit, all done, minus, if we plug in our lower limit, 0 cubed over 3 is 0. 9 times 0 is 0. So that makes this so much easier. If there was a negative 3 in there, it would be negative 3 squared, negative 27 with another negative. All kinds of opportunities to lose track of a negative and get the wrong answer. So those are just zeros. So let's see what we got here. So the 2 is outside the brackets. Negative 27 over 9, that's a negative 3 plus 27. Negative 3 plus 27. Ooh, hold the phone. That negative 27 over 9, that's x cubed over 3, right? That denominator's not a 9, that's a 3. I hope you're using pencil and not pen. There we go. That's a little better. Okay, now I can get rid of this, and let's get rid of that. So the 2 is outside. Negative 27 over 3, that's negative 9. I think I got that transposed in my head when I was sort of thinking ahead. And then we've got that plus 27. Negative 9 plus 27, that's 18, times the 2 we've had held out front there the whole time. 2 times 18 is 36. 36 square units. So there's an example of each for our even and odd function theorem. If it's even, you double it from 0 to the upper limit. If it's odd, the answer is just 0. And I think that's it. Yeah, next time I see you in class, we'll work on some odd problems and try these techniques out. I hope you found the video useful.